In this last section of Chapter 3, we're going to be taking a look at graphs, but not just any regular graph, graphs of derivatives. And of course, because we're not looking at regular function graphs and we'll be looking at graphs of derivatives, we'll have to kind of keep some concepts in mind that we've learned over this past chapter about what a derivative is and other things that connect to that concept. Okay, so this section is going to be all about taking a look at a graph from the point of view of it being a derivative, and then using what we know about a derivative to relate that to the original graph. So we're not going to be having graphs of functions in this lesson. We're going to be having graphs of derivatives, where we'll be asked to determine stuff about the original graph. So this slide will kind of serve as a resource of sorts so that you realize what you should be looking for. So quick review of these ideas. If a function is increasing, we know a derivative is positive. But because we're going to be looking at graphs, that would mean when your derivative or the graph is above the x-axis. Conversely, we know a function is decreasing when the derivative is negative. But we can take that one step further, and if we're looking at the graph of a derivative, that would mean we're looking for where the graph is below the x-axis, which is when it's negative. Relative maximum. We know relative maximums occur where the derivative changes from positives to negatives, if you think back to 3.3 and those sine charts. But now, since we're looking at a graph of a derivative, we want to see where the graph crosses the x-axis from the positive side to the negative side. Again, conversely, for a relative minimum, we're looking for where the graph of a derivative crosses the x-axis from negative to positive. One of the more important ones to kind of keep in mind, because it's easy to mix up this concept, is concavity. How do we know a function is concave up? Well, we know a function is concave up when the first derivative is increasing. And if you need a review of that concept, go back to the first slide of 3.4. If a first derivative is increasing, then we're trying to see where the graph has positive slope. Conversely, if a function is going to be concave down, we're looking for where the first derivative is decreasing. If we're looking for where the first derivative is decreasing, we're looking for where the graph has negative slope. So in these two ideas right here, which I would kind of star as maybe being ones that might be a little harder to grasp right away, is that we're not talking about a second derivative. We're using a first derivative to determine concavity. We could still use a second derivative, but in this case we're looking at the graph of a first derivative. So we have to understand fully what it means to have concave up or concave down. If we're trying to determine points of inflection, we're trying to see when concavity changes. And if you use the above explanation to kind of lead into this, we're looking for where the graph of the derivative changes from increasing to decreasing or decreasing to increasing. So again, use this slide as kind of a reference in case you kind of forget some of these ideas, but ultimately the best way to kind of see these in action is to look at a graph, which we'll see in this first example. Okay, so here we go. Starting from this point and really to the end of this course, every time you're presented with a graph, ask yourself one very important question. Is this a regular graph, like an f of x graph, or is it the graph of a derivative, like we have in this case? So we have A, B, C, and D that we have to address, so let's just go one by one and figure this out. So in part A, we want to figure out on what intervals is f increasing. Again, keep in mind, this is not the graph of a function, this is the graph of the derivative. So when we say increasing, we're not looking at this graph per se, we're thinking about what this graph would tell us about the original graph. So I think the best way to start these problems is to always justify first. If you justify first, you're doing two things. You're explaining, which most of these problems will always have you do, and you're also giving yourself the reminder of what you should be looking for on these graphs of derivatives. So we know a function is increasing where f prime of x is positive. So where is a graph positive? Now we can actually in a sense, disregard that this graph is a derivative and just ask ourselves, where would this graph be positive, from where to where? And you'll notice I'm going to kind of mark this graph so we can label it clearly. From 1 to 2, our graph is negative. From 2 to 4, our graph is positive, and I'm going to just kind of label the rest of these appropriately. So we always want to write our answers in interval notation. It's okay to use inequalities, but it's a lot quicker to use interval notation. So from where to where is the graph of the derivative positive? Our first interval is from 2 to 4, and our second interval is from 6 to 9. We're assuming that this graph starts, since we're not given any other information, starts and stops at these points. So I guess infinity could have been a possible answer, negative or positive in some cases. But in this case, it's starting at 0 and ending at 9. So our two intervals again are from 2 to 4 and 6 to 9. Part B. We want to find any relative maximums or relative minimums. So, like I said, I think the best thing to do is to justify first. We know relative maximums occur where the derivative changes from positives to negatives. At what x values does this graph change from a positive value to a negative value? We have 1. At x equals 4, our graph goes from positives to negatives. And of course, we're reading left to right. Relative minimum is kind of the reverse. Relative minimum is when our derivative changes from negatives to positives. Graphically speaking, that's when we cross the x-axis from negatives to positives. And that happens at 2 points, at x equals 2 and at x equals 6. Part C. Where is the original graph? On what intervals is the original graph concave up and concave down? Again, just like I start that in the last slide, I think this concept is one of the more challenging ones to confuse with maybe parts A and B. But if you just keep in mind that concave up is where the first derivative is increasing. Again, we have no information about a second derivative, so we're not really thinking about that. So concave up again occurs where our first derivative is increasing. I'm going to use some arrows now to indicate increasing and decreasing. So you can see our graph is increasing in these 3 intervals. What are those 3 intervals? From 1 to 3, from 5 to 7, and from 8 to 9. Conversely, concave down is where the first derivative is decreasing. Again, if you need that kind of review of these ideas, please go back to 3.4 for concave up and concave down. Where is this first derivative graph decreasing? Well, that's when the graph is going downward. And there's 3 regions for that as well. From 0 to 1, from 3 to 5, and from 7 to 8. The last thing we need to address is, are there any points of inflection? So the interesting thing about this question is, where we used to identify relative maxes and mins, if this had been the original graph, if this was the graph of f of x, that would have been a relative min, that would have been a relative max, relative min there, relative max there, relative min there. But you gotta be careful. This is the graph of a derivative, and the graph of a derivative changes from increasing to decreasing, which would indicate a point of inflection. So a point of inflection occurs where concavity changes. Concavity is changing from 0 to 1, where it's decreasing, and 1 to 3, where the first derivative is increasing. So again, kind of keep in mind that these relative maxes and mins in this picture, if that had been original function, would be relative maxes or mins, but in this case they're actually points of inflection. So again, we have these points of inflection at 1, 3, 5, 7, and 8. Okay, here's another example. We have a graph. So again, I would always ask myself the question, is this a regular graph or a derivative graph? And you can see that it is a graph of a derivative. It goes from -7 to 7, so it doesn't keep on going outside of those 2 values. And we know we have horizontal tangents at -3, at 2, and at 5, and a vertical tangent at x equals 3. In part A, we want to identify any relative minimum and then justify our answer. So just like I did in that last example, I'm going to go ahead and label the values that this graph has. So in that first section it's positive, second section negative, and then the rest is positive. So we know a relative minimum occurs when the graph changes, and we've got to be specific, it's the graph of a derivative. We know that if the graph of a derivative changes from negative values to positive values, we have a relative minimum. And in this case, you can see that happens at one x value. At x equals -1, our graph changes from negatives to positives. Part B, basically the same as part A, but now we need to identify relative maximums. In this case, it's kind of reverse of part A. We know that there's a relative max at x equals -5 because the first derivative, f prime of x, changes from positives to negatives. The last part of this question is for us to figure out the values of x, where the second derivative is less than 0 or negative. If the second derivative is less than 0 or negative, that's just another way of saying concave down. And if you recall from the last slide and from the slide before that, we know an original graph is concave down when the first derivative is decreasing. So we can state the second derivative is negative when the first derivative is decreasing. So again, like the last example, I'm going to put some arrows to indicate where it's going up and down. But this one right here, don't draw that last red arrow that I drew in right away. Technically, that's not quite right. Back from the original problem, they state that we have a vertical tangent at x equals 3. So I'm going to draw that vertical tangent in. And the reason that's important is because we need to split that arrow that's going down into 2. It's going down from 2 to 3, and then 3 to 5. Right at 3, since it's a vertical tangent, it can't be decreasing there. Okay, so let's go ahead and identify the x values for where the first derivative is decreasing. So the first interval is -7 to -3. The second region, which is the little shorter arrow, is 2 to 3. And then the last region is 3 to 5. So had you wrote 2 to 5 like we originally put and didn't take into account the vertical tangent, you would have missed out on a point there. So we had to split that into 2 sections because of that vertical tangent. Okay, in this slide we're going to try to prove why the derivative of sine is cosine, and in the second example, prove why the derivative of cosine is negative sine. And we're going to do that visually using this idea of the graph of a derivative. So first one is the derivative of sine is cosine. So there's the graph of sine, and we're going to graph both the original function and the derivative in this one graph so we can kind of see how one can indicate something about the other. So one thing you're going to have to keep in mind is when you're dealing with a regular graph, when we make a table of values, one's x, one's y. We already know that, just like you see right here. But since we're trying to make the graph of a derivative, that table is not x's and y's, it's x's and slopes. So be careful. Those y values, which are still going to be plotted the same way, really indicate slope. Okay, so let's take a look at this graph and identify the slopes so we can plot these points. At the x value of -pi, what would the slope be? Well, you can see the graph is going downward at some sort of value. And just for the lack of explaining the specific reasons why, that slope I'm going to say is negative, and the value on that will be a 1. At that point, the slope is -1. And I'm going to go ahead and place a dot there. We're going to plot this as we go. So at -pi, we have a dot at -1. What is the slope at -pi/2? Well, you can see it highlighted in yellow, and you'll notice that would be a horizontal tangent right there, which would tell us we have a slope of 0. So the corresponding slope would be 0 there. And again, we're going to plot these points as we go, so I'm going to put a dot at 0. And again, keep in mind, that is indicating slope. What is the slope at 0? Well, just kind of like at negative pi, you saw it was negative 1. At 0, it's going upward, it's increasing, so that's going to be a slope of positive 1. Go ahead and place a dot up at 1. At pi over 2, again, we have another one of these horizontal tangents. We know the slope is 0 at that point, so 0 is the slope, and we'll put a dot at 0. And the last point that I'm going to use at pi, our slope is going downward again, just like we saw at negative pi, so that slope is negative 1. Put a dot down at negative 1, and sure enough, if you connect these dots with a smooth curve, we get the graph of cosine. So we know now that the graph of sine, or I should say the derivative of sine, gives us cosine. And visually you can see that right here. So just to kind of indicate a couple things real quick, you can tell right here our graph of a derivative changes from negatives to positives, which indicates a relative min. Right here, the graph of the derivative changes from positives to negatives, which means relative max. So you can see how those two interacted right there. From here to here, the graph of the derivative is increasing, which means our graph of the original function is concave up. Here the graph of the derivative is decreasing, so we know our original graph would be concave down. So I made the graph a little bit messy by indicating those things, but you can see how now the graph of the derivative is telling us things about the original graph. Okay, let's take a look at this other one, and I'm going to go through this one a little bit faster since it's the same basic idea. The graph of, or the derivative of cosine is negative sine, and just as a reminder, that negative in front of the sine means our sine curve should be reflected about the x-axis. So if I pick some points here and find the slopes, we can graph our derivative. So at negative pi, our slope is 0, so I'll put a dot at 0. At negative pi over 2, our slope is 1, so I'll put a dot up at 1. At 0, our slope is 0, so I'll put a dot at 0. At pi over 2, the slope is negative 1, so I'll put a dot at negative 1. And at pi, our slope is 0, so I'll put a dot at 0. And sure enough, when you connect those dots, that's the graph of negative sine. So just to indicate some important things here, you'll notice our graph of the derivative crosses the x-axis right here from positives to negatives, which means we have a relative max, which checks out. You can see that the graph of the derivative is decreasing right here, which would indicate that our original function has a concave down in that corresponding interval. So again, just a good little way to prove why the derivative of sine is cosine, and why the derivative of cosine is negative sine, but also more importantly to indicate how the graph of the derivative tells us things about the original graph. Okay, continuing from the last slide, we're going to be taking a look at graphs of functions and the graph of their derivative all in the same picture. And in this case, we just have a basic linear function as our f of x. And if we were to take a look at the graph of the derivative, you'll notice that is just a constant horizontal line. And that makes sense because the graph of the original function has a constant slope. So I suppose if the slope of this line was 2, then f prime of x, the graph of the derivative, would go through the value of 2 as a horizontal line. When we get to the more curvy looking functions and we take a look at the graph of the derivative, you'll notice that at this point right here, which we know to be a relative max, the graph of the derivative would have to cross the x-axis from positive values to negative values. And then kind of the same thing will happen over here. At this relative min, we know that the graph of the derivative would have to cross the x-axis from negative values to positive, which we can see there. So you can see how these features of the graph of the derivative tells you things about the original graph. On the graph of the absolute value function, it's kind of like the linear function from right above, except on the left side of the origin, the graph has a negative slope, so that derivative would be below the x-axis, and on the right side of the origin, the function has positive slope, so that would mean the graph of the derivative would be above the x-axis. And of course at 0 with that sharp corner, that would make the derivative undefined. In this last one, again, you'll notice that right here we have a relative x, and the graph of the derivative at that same x value crosses the x-axis from positive values to negative. Over here at the relative minimum, the graph of the derivative crosses from negative values to positive values, and at this other relative x, you can see that the graph of the derivative crosses again from positive values to negative values. So hopefully these 4 examples with the last examples on the last slide kind of give you a good idea of how these graphs of derivatives tell you things about the original graph. The last thing we have to talk about in this lesson is actually graphs of second derivatives. From time to time you'll run across these, or you'll actually find that graphing a second derivative can actually be more helpful than looking at the graph of a first derivative, possibly. But in this first example here, we have the graph of a second derivative, and I want to find the x-coordinates for inflection points. So if you think back to when we first learned about this in 3.4, points of inflection occur where concavity changes. That is to say, if I drew out a sine chart, we would want to see a concave up change to a concave down, or a concave down change to a concave up. But ultimately, what you are hopefully keeping in mind is that a second derivative has to change signs, either from negative to positive, or positive to negative. So when we're talking about the graph of a second derivative, we're really just trying to figure out when do the values go from a negative to a positive or a positive to a negative. And based on what we saw from these first derivative graphs, we know that happens when the graph crosses the x-axis. So I'm going to again, kind of like you saw me do, label the values that we're dealing with in this particular graph. And you'll notice at x equals 1, there's a point of inflection, because we changed, our second derivative, I should say, changed from negatives to positives. We also have a point of inflection at x equals 7, because our second derivative values changed from positives to negatives. In this last example, we have a multiple choice question from the AP exam. Very common question in a sense, where using the first derivative might be fine, but maybe using the second derivative graph could be a little more helpful. So we have a function f that we don't know that goes from negative 1.5 to positive 1.5, and we have this derivative for the function right here. I want to figure out on which intervals the graph is concave down. My kind of point of view on these problems is when you're dealing with concavity and you can actually get a second derivative, I would think it's a little bit easier to do with the second derivative graph, but you could actually do this with the first derivative graph if you had to. So when you're asked about determining concavity or points of inflection, I think it can be easier to use the graph of a second derivative instead, but it's not a requirement. So for the sake of practicing this, we're actually going to take a look at the graph of a second derivative. So if you've been practicing using your TI-89, this shouldn't be too difficult. So if we're trying to graph the second derivative, we need the equation of the second derivative. So if you take the time to type in this first derivative into your calculator and then carry out the proper notation for taking a derivative, you should find that the second derivative of our function here is given by this equation. This is our second derivative. And if you use the little copy-paste thing, because typing this out in y equals is probably not a good idea, if you highlight this and copy and paste it into y equals and graph it, you should get a graph like this. And just keep in mind, always restrict your window to the interval that the problem cares about. And in this case, we're just going from negative 1.5 to 1.5. So I set these little intervals to be 0.5. Okay, now I guess to the most important thing here is, where is this graph, or where is the original graph, I should say, concave down? And kind of the simple justification we can do here is this. We know a function is concave down where the second derivative is negative. How do we translate that into what we need from this graph? Well, the second derivative is negative when the graph of the second derivative is below the x-axis. This graph is below the x-axis in this region and in this region. And if you look at these values here, you'll notice that it's from negative 1.5 to negative 1 and 0 to 1. So just to kind of recap, we could have still done this with the graph of a first derivative, but it might have been a little bit more difficult, potentially, to identify these intervals. With the graph of a second derivative, it actually is fairly straightforward and pretty simple in comparison maybe to the first derivative.